So in this video, we're going to talk about integration by partial fractions. So first of all, what are partial fractions? So partial fractions, it's really the process of taking something that looks like this, 5x minus 3 over x squared minus 2x minus 3. So it's the process of taking this and rewriting it as this expression here. So notice my two denominators, x minus 1 and x minus 3. That's exactly how this factors here. So we have like a specific way on how we can rewrite these, and this side is easier to integrate than this side. So do you always have to use partial fractions? No, but it's one of those methods that if nothing else works, you might want to try partial fractions. So let's talk about just some ground rules of partial fractions. So if you have something in the form f of x over g of x, first of all, the degree of the top, f of x, needs to be less than the degree of g of x. If it's not, then you need to use long division. So we'll be checking for this, and if the degree is either equal or greater than, then we'll have to use division, and we'll review how to do division when we get there. Second, we need to know the factors of g of x. So hopefully you're pretty good with factoring. If you feel like you need a review on that, I do have other videos on that you can check out. All right, so there is a pattern to partial fractions. We will summarize the pattern at the end. But for now, what I thought is that we would just start going through a bunch of examples, and then we'll summarize the pattern at the end. Okay, so let's start with 3x plus 11 over x squared minus x minus 6. So the first thing that you're going to want to do is you're going to want to factor the denominator. And this will factor as x minus 3 and x plus 2. Okay, so the next thing that we're going to do is we're now going to write out the form of our partial fractions. So the form of the partial fractions is the part that has the pattern. So I'm just going to show you several different forms in this video, and then like I said, we'll summarize them at the end. So when you have two different linear factors, so these are two linear factors, what we're going to do is each factor gets its own coefficient, a and b. So ultimately, I want to figure out what a and b is that will equal this original rational expression. Okay, so what we're going to do next is we're going to multiply everything by this denominator, x squared minus x minus 6. So think about what happens when you multiply. So when I multiply this x squared minus x minus 6 against this, what am I left with? The x minus 3's will drop out, so I'm just left with a times x plus 2. And then when I multiply all of this times this fraction here, this b over x plus 2, the x plus 2's will drop out, and I'm just left with this x minus 3. So this becomes b times x minus 3. And then when I multiply this fraction by this denominator, obviously the whole denominator is just going to drop out. And so I'm left with 3x plus 11. So now I have actually set this up in a way that I can actually solve this. So let's make a little space. And okay, so there's a couple ways in how you can do this. So we'll start by doing this the long way, but you can probably, like after you see it, you might see some ways to do this the shorter way. So what we can do is we can go ahead and we can distribute everything. And so ultimately what we want to do in this line of stuff is the x terms all need to be equal to one another, and the number terms, so just the plain terms, need to all be equal to one another. So I'm going to have ax plus bx equals 3x, and 2a minus 3b equals 11. Now, in this case, we can drop the x's. We don't need the x's to help us out with this. So now what I'm going to be left with is actually the system a plus b equals 3 and 2a minus 3b equals 11. And so what's going to happen with your partial fractions is you're going to end up with systems of equations. So they'll often be 2 variables, 3 variables. It's kind of the Wild West, and anything can happen. But then you're just going to think back to your old algebraic techniques of how would you actually solve for this. And if you're rusty, you actually might want to pause here just to give it a go and see if you remember. Worst that happens is you don't remember and I show you. So what I'm going to do is I'm going to use the elimination method. So I'm going to multiply this top equation by 3. So this is going to become 3a plus 3b equals 9. And then I left the bottom equation alone, but now I can use elimination. So the b's end up dropping out, and I'm left with 5a equals 20. So what that means then is my a equals 4, and now I can use this in either one of my equations to solve. So I'll use it in the first equation. So I have 4 plus b equals 3, so that will imply that b equals -1 if I subtract off the 4. So now I've solved for my a and for my b, and so now I can put that back in. You might remember when we set this up here. So now I'm just going to replace my a and my b. So I'll just make some more space. So I have 4 over x minus 3, let's see, minus 1 over x plus 2. So here's what I'm integrating now. And this is much simpler to integrate than what we had before, because before, if you tried to use substitution or anything, it really wouldn't work. So now I can just integrate this as is. You can either use substitution for this, or if you're used to the pattern with this, you can go ahead and finish this. Just for the sake of time, I'm going to go ahead and just write out what the final answer is. So I'm going to have 4 times the natural log of x minus 3 minus the natural log of x plus 2 plus c. Okay, and I just want to remind you, so this was the setup for when we had 2 separate unique linear factors. So now we're going to look at a slightly different example. So now I've got 3x minus 2 over x squared minus 2x plus 1. Again, if you were to try to use substitution here, it wouldn't work. So what we're going to do is first we're going to factor the denominator, and this factors is x minus 1 times x minus 1. So when you have repeated linear factors, the setup is going to change slightly, okay? So the way that this setup is going to work is I'll have a over x minus 1. Actually, I don't need anything for that one. And then b over x minus 1 squared equals 3x minus 2 over x squared minus 2x plus 1. Okay, and so this is now just the setup in this case is so when your factors repeat, then you keep putting each factor underneath however many times it repeats. So this one repeated twice, so the second one gets a squared. If this repeated 3 times, then I would write a third factor of c over x minus 1 cubed, so it's just kind of so on and so forth. So now we have all of our factors here, so we can go ahead and solve. So what I'm going to do is I'm going to multiply this by all the fractions here. So what I would recommend to you is I would actually write out what are we left with, like what are we actually trying to solve. I would do that next before I show you and then hit play. So in multiplying this by the first fraction, I'm left with a times a minus 1. But in multiplying this times the second fraction, this x minus 1 and this cancels out with itself, right? So this becomes equals b, and then this is 3x minus 2. So here's what we need to solve. Now, one thing that I tend to do is I'll kind of shortcut this as I look through this. So what I'll notice is that I've got this a bouncing off this x, and I have a 3 over here. So I'll just set this up as a equals 3, and then I'll do it again. So I'll take a times the -1, and then the b, just assume the b is times a 1. So those are my 2 number terms. So this would be -a plus b equals -2. So this is just a way to shortcut everything. However, I will, just in case anybody wants to see all the work, I'll show you also the long way. So let's make a little space. And so let's see, I have ax will equal 3x, and -a plus b will equal -2. And so then I can compress this into a equals 3 and -a plus b equals -2. And now as you can see, right, so this actually already told us what a equals, so then I just have to solve for b. So I have -3 plus b will equal -2. So if I add the 3 to each side, I'll get that b equals 1. And so now my new integral will be 3 over x minus 1 plus 1 over x minus 1 squared dx. Okay, so let's make some space. And now we can go ahead and integrate. So this first one is just going to be, so let's see, this one here, this just is going to be 3 natural log of x minus 1. For this second one, so we are going to have to use substitution here. So for this one, so what I'll do is I'll set my u equal to x minus 1. So my du will just be dx. So I can set this integral up then as du over u squared. And so that will be negative u to the negative first. So this will just equal x minus 1 to the negative first. So all in all, let's see, maybe I'll just put a line there. So this becomes plus, actually minus, sorry, supposed to be a minus in front there. Minus 1 over x minus 1, and then plus c. So that would be everything for that one. Okay, so just to remind you again, so that's what we did for now repeated factors, linear factors. So the more they repeat, the more terms you have to write. So now let's talk about what do you do when you have irreducible quadratic factors. So what do I mean by that? So first of all, what I want you to do is I want you to pause and I want you just to factor the bottom. I want you to think about it for a second before I tell you. So go ahead and factor the bottom. So the bottom will factor actually as x squared minus 2 and x squared plus 1. So in this case, I have 2 unique irreducible quadratic factors. And what I mean by irreducible is I can't factor either one of these anymore. Not nicely, right? So that's going to help us set up for our next part of this. So for irreducible quadratic factors, so the setup now is instead of just being an a, it's ax plus b. So we're going to have ax plus b over x squared minus 2 and cx plus d over x squared plus 1. So those are going to be the setups for this next part. And it's going to be that same setup again, now where I multiply this denominator against everything. And so once again, just to check that you're actually like getting this, I'd like for you to try that on your own before I show you. So maybe pause and then hit play. So what I'm going to be left with is ax plus b. So I multiply this denominator by the first fraction. So the x squareds minus 2's will drop out. So I'm left with x squared plus 1. And then I have this cx plus d, and that's going to be x squared minus 2. And all of that will equal x. So I'm kind of running out of space here. Okay, let's see. Actually, I'll cram it in over here. Okay, so let's make some space. Okay, so now at this point, this is also where I kind of like to advocate for having a better way to organize yourself, because yes, you could technically FOIL everything out, but you're just gonna like explode in letters. So if you want to FOIL everything out, that's not a problem. But what I'm gonna do this time is I'm just gonna show you like a potential shortcut that you could consider if you don't want to just explode your page with a billion variables everywhere. So what I'm going to do is I'm going to kind of FOIL, but I'm going to be strategic. So what I'm going to do is I'm going to take this first term and I'm just going to set up what it would mean to multiply by this entire other bracket. So I'm going to set this up as ax times x squared plus 1. Okay, and then I'll continue on to the b. So this will be plus the b times x squared plus 1. And then we'll repeat that process over here. So plus cx times x squared minus 2. And then d, let's see, I'm running out of space. So plus d times x squared minus 2 equals x. And then the other thing that I want to do is just where I have that x in front, that x is the only thing that I'm going to distribute into my parentheses. So what I'm going to get now is a times x cubed plus x, b times x squared plus 1, c times x cubed minus 2x, and d, let's see, I'll just continue on to the next line, and d times x squared minus 2 equals x. Okay, so now what this allows me to do is I can kind of pick and choose the information that I need. So notice that on the other side, the only variable that I really need is going to be x in this case, right? So what I'm going to do is I'm just going to look for all the x terms. I have an x here, I have an x here, and I have an x here. So if I bounce those x's off of their respective letters, so what am I really going to be left with? I'm going to have a minus 2c, that should equal 1. So that's ax plus negative 2cx equals 1x. And I've just gotten rid of all the x's and just written it like this, okay? So there's one part. And I still have to set up these other equations. So let's see. I have my cube terms. So I have a cubed, and then where's my other cubed? C cubed. So that's going to be a plus c equals 0. And then let's see. So I have my squared terms. So I have this bx squared and this dx squared. So that's going to say b plus d equals 0. And then finally, b jumps off of this 1 and d jumps off this negative 2. So this will be b minus 2d equals 0. So here's the little weird system that I have now. And so in this case, like with this first one, so what you're going to find for these is that since everything here is equal to 0, you're going to get that b and d equals 0. So you can go ahead and take the time to solve the system, but you will just get that everything equals 0. So this other system is really now what I need to focus on. So let's make some space. And then we can just solve using our typical methods. So let's see, I'm going to set this up as, how about a minus 2c equals 1 and 2a plus 2z equals 0, 2c equals 0. So what I get then is 3a will equal 1 if I use elimination, so my c's drop out. So I have that a is equal to 1/3. And then if I use this equation here, so 1/3 plus c equals 0, that will imply that c equals negative 1/3. And so there are my two constants then that I'm going to fill in ultimately into, remember, this whole form here. So my b and my d were equal to 0. So let's just go ahead and set everything up. So what I've done here is I've just plugged in all the numbers that we just found. And so this is just to show you everything plugged in. But this is kind of an inefficient way to really set this up because these zeros are not really adding anything to the problem. So these 1/3, these can actually be factored out and turned into their own little integrals. So this will be 1/3 x over x squared minus 2 minus 1/3 x over x squared plus 1. Okay. And so from here, for both of these, really now you can use substitution. So I'll just do one of them just for the sake of time. So for this one, my u will be x squared minus 2. My du will be 2x dx. So 1/2 du will be x dx. So I can then set this up as 1/3, take that 1/2 out. So it'll be 1 over u du. So this comes out to 1/6 times the natural log of x squared minus 2. Okay, so that's for one of these. So for this other one, this will come out to negative 1/6 natural log of x squared plus 1 for very similar reasoning. So the final answer, so just to make it clear what the final answer is, my final answer will be 1/6 times the natural log of x squared minus 2 minus 1/6 times the natural log of x squared plus 1 plus c. Okay, and so for our final one, so now I just wanted to talk about what do you do when the top and bottom have either the same degree or they have a higher degree, or yes, same degree or higher. So in this case, I have x cubed and x cubed, so that's like a no-no for this, right? So we're going to have to use polynomial long division. Now, if you're rusty on polynomial long division, I've created a review video specifically for calc students just to like brush you up on that in 10 minutes or less. I think it's about 10 minutes. But I'm going to just do a quick review here. So the bottom is what we are dividing with. So I'm going to set up the long division here into x cubed minus x. This is going to be x cubed plus 1. And so to work through this, what you need to do is you ask yourself, so you just pay attention to the first terms. What do I have to multiply x cubed by to get to x cubed? And in that case, the answer would just be 1, right? So x cubed times 1 will equal x cubed. So then what I'm going to do is I'm going to take 1 times this entire part, and this will be x cubed minus x when I multiply that out. And then I need to subtract this off. So in subtracting this off, what ends up happening is the x cubes cancel out. Don't forget to distribute this negative. So this will just be an x here. And then what I'm going to do is I'm going to bring this 1 down. So this doesn't seem like much for a division, but now this actually sets us up so that we can work with this. Because that remainder of x plus 1, now I'm just going to put it over the divisor. And this meets the criteria that we need to use partial fractions with. So this is equivalent to this, but now we've kind of made it a little bit easier to work with. So let's restate our integral now like this. So there's what I'm integrating now. And of course, integrating the 1, that one's going to be easy peasy. So let's just focus on how do I get my partial fractions here now. So for x cubed minus x, that's going to factor as x times x squared minus 1. And I can factor that again as x times x minus 1 times x plus 1. So I think this is actually a great one just to try on your own. So give it a try and then hit play when you're ready. And I will show you the solution whenever you get stuck. So what I'm going to do is I'm going to set up my partial fractions. So I've got a over x, b over x minus 1, and c over x plus 1. And now I'm going to set this equal to x plus 1 over x cubed minus x. So now I'm going to multiply everything by x cubed minus x. So this is going to become a times x minus 1, x plus 1. This will be bx times x plus 1. And this will be cx times x minus 1. And all of that now is going to equal x plus 1. So once again, this could be a good case for not just exploding everything out, but instead of just kind of leaving those letters there. So what I'm going to do is I'm just going to multiply the x's together. So this becomes a times x squared minus 1. This will be b times x squared plus x. And this will be c times x squared minus x. And this equals x plus 1. And so now what I can do is I can kind of just match up what corresponds with the x and the 1. So I'll make a little bit more space. Okay, so first I'm just looking for anything with an x with it. So those are the things that have x's. So that's going to come out to b minus c equals 1. Then I'm going to look for just the number parts. So that would just be this part here. So this will be negative a equals 1. And then I have just kind of these other parts. So let's see, what else do I have? I really just have the x squared parts. So this says that a plus b plus c equals 0. Okay, so the good news is that we've already solved for a, right? So from this a, negative a equals 1, what we get right away is that a equals negative 1. So now I can just solve this b minus c. So I'm just kind of finagle with this, right? So this will be b equals 1 plus c. So let's see what happens if I put all this information into this equation here. So my a will be negative 1, my b will be 1 plus c, and then we'll just have plus c equals 0. So this gives me that 2c equals 0, so that must mean then that c equals 0. So now I'm going to use this c equals 0 and this a equals negative 1 in this equation. So let's see, so then I'm going to get negative 1 plus b plus 0 equals 0. So that means that b must equal 1. Okay. And so now we've got kind of all those pieces here, right? So let's see, let's go ahead and write this out. So my a was negative 1 and that went over the x. my b was 1, and that went over the x minus 1, and then my c was 0, so that went over the x plus 1. So here is what I'm going to integrate, and obviously I don't need that 0, right? So that part can just drop out entirely. So then this will become the negative natural log of x plus the natural log of x minus 1 plus c. So that's one part of the integral, but wait, I forgot about the other part. So the initial integral was this, so also don't forget about that plus 1. We never integrated that. So actually before I put that plus c, I also need to add an x and then a c. And now we've got everything integrated. Okay, cool. So let's summarize now, and I didn't do the last part of this because it's a little redundant and not needed, but I think you kind of see the pattern. So when you have an individual linear factor, so something with just an x in it, then each independent linear factor gets its own factor, so a over x plus b. So each time you have a unique one, it gets its own factor. Now when factors repeat, then you also have to repeat them in that partial fraction decomposition. So in this case, if I have like k of these ax plus b terms, so these are all linear, so they just have an x in them, then I have to repeat that k times, and you just put up a letter on top for each until you've gotten all k of those factors. Now if you have an irreducible quadratic factor, something of the form ax squared plus bx plus c. So the idea here is that this cannot be factored further. That's kind of one of the keys. When this happens, then what you put on top is ax plus b for each one of those factors, right? So we just saw one where we had two different quadratic irreducible factors, so we got an ax plus b and a cx plus d. If any of those quadratic factors were to repeat, you do a very similar thing. You're going to have ax plus b1 over that factor, ax plus b2 over that factor squared, and if you have that k times, you'll just repeat it k times. So this is a little summary of everything that we just talked about. Now, as a reminder, I do have a lot more example videos, so if you want to watch more examples of just different ways of solving the systems and all that good stuff, please check those out. If you found this helpful, I'd love it if you hit the like button or the subscribe button. And otherwise, I will talk to you guys in another video. Bye!